Hi everyone. We have done a couple of classes and we started with analog circuit, right? And we started with amplifier modeling. We modeled amplifier as a dependent source, and we got to see we have got four kind of basic amplifiers: voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. And we also modeled some circuits, equivalent circuit, right? And thereafter, we started one of the very important topic, that is op-amp, operational amplifier. And we got to see various modes such as negative feedback mode. And we got to see two kind of operations, linear and non-linear. And we have seen uh, inverting and non-inverting amplifier. And we calculated gain and we calculated output under some ideal conditions, right? If op-amp is ideal, then it has huge gain, right? And it has high input impedance and low output impedance, right? So today, and we have solved various problems related to op-amp. So today, what we are supposed to discuss here is the how to determine input and output impedances or resistances of an amplifier using op-amp, right? So the topic of today's discussion is going to be the input, input and output, okay, resistance of resistances of an amplifier using op-amp, using op-amp. So the amplifier here is going to be what? Amplifier will be here the op-amp, and we have to what? We have to take the we have to find or determine the input and output resistance of that. Okay, input and output resistance. So the amplifier which we have discussed is op-amp only, right? The operational amplifier. So how we determine basically the input impedance, right? Suppose we have got this kind of a two-port network, okay? TPN you can say, two-port network, okay? And we have got one port where we have connected the source here, right? And there is some load, right? You can see this is a load RL, okay. In the network analysis, we have seen, okay, this kind of a two-port network, and if there is input connected, right, the voltage is connected here, V in, okay, in the input port, plus to minus, and this is R in. Sorry, this is not R in. This will be I in. If current is flowing here, right, so just forget about this resistance. Uh, just connect here directly, and the current is flowing I in, right? Current is flowing I in. So you can say that if you're looking from this, okay, if you're uh, looking from the input port, so you will find that the ratio of current, the voltage and the current, right? The V in by I in, right? V in by I in is going to be giving you the input resistance, okay, of any kind of amplifier, because amplifier will be having different ports. The input port where the input is applied, and the output port where the output is taken, right? And the power port where the power supplies are given, right? To power up the amplifier. So this is how we determine the input resistance. Just apply one input signal and allow the current to flow and take the ratio of them, and you will get the input resistance of that amplifier, right? So this is how we treat or we treat two-port network to determine the input resistance. And second is output resistance. How to determine output resistance? output resistance, right? So in order to determine output resistance, we have seen already finding equivalent resistance in case of different big networks using certain theorems such as Thevenin theorem, Thevenin equivalents, right? Or Thevenin theorem, we can say if we have got two-port network again, the TPN, right? TPN. So what we will do here is, in case of output resistance, we have to consider this resistance as Thevenin resistance. Okay. Yes. Welcome, Surajit, to the class. So we can get back and uh, you know, like yesterday, I said that I'm going to talk about input resistance and output resistance of an amplifier using op-amp, right? So that's what I started with today's class. And I told that if there is a two-port network, and if this is an input port and this is the output port, and if we connect some voltage source and if there is a current, okay, if we take the ratio of them, so we'll get the input.
Good morning, sir.
Yeah, good morning, Surajit. Yes. Uh, okay. So please note down this topic, input resistance and output resistance of right? Uh, Right now, we are talking about operational amplifier, but in future you will find that we will also use bipolar junction transistor or MOSFET metal oxide semiconductor amplifiers, right? In a different uh, configurations and different biasing, right? So you will just determine the input and output resistance in using the same procedure. Okay, so this is what the input resistance, input resistance, input resistance, right? Okay. Output resistance, suppose this is a two-port network. Output resistance, you can also call it as, you know, Thevenin equivalent, right? Thevenin. The way you find Thevenin resistance, okay, Thevenin resistance, right? The way you find Thevenin resistance, the similar procedure you have to follow here as well, right? So you have to deactivate input, source by its internal resistance. If there is voltage source, you have to deactivate by short circuit, okay? And if there is a current source, you have to deactivate it by open circuit. And you have to what? You have to apply some test signal here, right? Test voltage. Here you have to apply some test voltage. You can apply some V test, okay? V test, right? And then there will be a current flow, that is I test, right? And take the ratio of them. If you're looking back to the two-port network, so the resistance which you will measure here, that is R out, will be, you know. Now you might be wondering why we are applying V test. As we know that the amplifier will be having the dependent sources. Amplifier is modeled with the help of dependent sources. So if you might have studied in network theory, that network analysis or electrical engineering, that if there is a dependent source, so we need to connect uh, you know, we need to connect one test voltage and then take the ratio, right? So V test upon I test. Okay. So this will give you output first. I hope this is clear. Or you can also put 1 volt as a test voltage and allow the current to flow, right? So three procedure you have to follow. I mean, three steps in that procedure to determine output resistance. Open circuit load, just remove the load, right? And second one, short circuit the V in, right? Or you can say, or open circuit, uh, you know, current source, right? You can say current source. Okay. And the third one will be connect, you know, you can connect here, connect 1 volt, okay, as a source, 1 volt source of, okay, 1 volt source at output terminal, right? At output terminal. And then you can measure the R out. R out will be what? V 1 upon I, right? I in you can say. Sorry, uh, I test or whatever you want to call it, right? R out you can say. So, I out, sorry. So this is output resistance, okay? Now let us take one problem here, then you will understand everything. So Surajit, have you understood these two concepts, how to determine input resistance and output resistance? Yes? Okay. So let me take one example, then you will understand things. Okay. So the very first example is determine the input resistance of a given amplifier. So your amplifier looks like this. Please draw with me the amplifier plus minus. This is V in, right? And there is a resistance, and there is a again one resistance, that is feedback resistance is given, and there is a V naught. Okay. So you can say this guy is RF, okay, and this is R1. This is this. Now you have to find the input resistance. Okay. Input resistance means from where you have to look back to the amplifier. You have to look back to the amplifier from the which terminal? Can you tell me? Because the input is applied at non-inverting terminal, right? So you have to look from here, right? If you're looking from here, so you have to find R in. In case of, while finding R in or input resistance, you don't have to deactivate anything, or you don't have to replace any voltage source or a current source with the help of its internal impedances. Okay. So you see here, as far as we know that op-amp does not draw any current, right? So here the I in will be what? I in will be 0, right? I in will be 0. So what you can say here is that the Rn will be Rn equal to V in by I in, right? V in by I in. So V in, what is I in here? I in is 0, means the input resistance of this amplifier will be infinite. Okay.
Yes, sir.
Hmm. So you are looking from the input term, non-inverting terminal, right? Looking from. This word is very, very important. From where you look exactly, that is important. Suppose you have to find the output resistance, so you will have to look back to the amplifier, right? Look back. Okay. This is first example which I wanted to discuss. So let me take a second example. Draw the circuit with me. The circuit looks like this, very easy circuit. Uh, this is minus, these are the op-amp signs, and this is the ground here, and there is a resistance. Now, this time they have given this kind of a T network for feedback resistance. Okay, and this is directly connected to output, right? And there is a connect. Okay, this is input here now. This time input is connected to the inverting terminal of the op-amp, and this is how the things look like. Okay, and the R1, this is R1, and this guy is R2, this guy is R3, this guy is R4, right? Okay. So can you tell me, Surajit, what shall be the input resistance of this amplifier? How you can determine
It's
input?
R1.
Yes, great, great. So this voltage will be here 0, right? and the current will be flowing V in by R1. And if you want to find the input resistance, so the Rin will be equal to R1. Very great. Needless to find anything. Okay, so if you're looking from here, you will get this.
Sir,
Yes, 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 yes. Yeah.
sir, if VGC is not applicable or the internal gain is maybe finite, so in that case we have to analyze the whole circuit for finding the Rin.
Yeah, then you will have to draw the equivalent circuit. You will have to bring back the, you will have to replace this op amp with the help of DCVS. Okay. The voltage control voltage source you have to bring in, right? Or understand? I
Sir,
mean, you
what's
will have, yes.
of the op amp in that case?
What? Can you
In
repeat that?
that case, how can I get the output impedance of the op amp? Because if it is not given in that case, means
Uh,
in voltage source, voltage control voltage source, it is some output impedance is there.
yes, yes, yes. See, whenever op amp is not in ideal condition, right? Whenever op amp has finite gain, we will come to that. And so what you have to do here is you have to replace this op amp with the help of its equivalent, okay? And then you have to apply the same concept, right? You have to apply the test voltage if you want to determine the output resistance, and then apply some KVL, KCLs, whatever laws are there. So you will get that, okay? So whenever the question will be there, we will discuss. But most of the time in the gate examination, they will an HAL or BARC, right? They will ask this easy question only, right? I mean, otherwise it will become lengthy. Okay.
Okay, okay, sir.
We are
That's become
coming to
lengthy
that.
actually.
Yes. Few questions.
Okay, sir.
Huh. You have to replace the equivalent. Otherwise, there is no other procedure, right? Uh, Example number 3. So whatever question we are taking here is the assumption is that the op amp is ideal. This circuit, one of the very beautiful circuit I'm drawing now. So please draw with me, and this guy is V in, right? Now there is a voltage divider. This is a voltage divider, okay? This is connected from here to here, and now this time this is also connected directly to the output, okay? So this guy is V out. And now this is 10K this time. This is 20K, and this is 5K. Very quickly, please determine the Rin. So from, you have to look into this, right? From here, you have to find Rin from here, right? So this question is very good question. Consider that the op amp is ideal. So please try this question. I will also solve along with you. So in the network itself, we can uh, say something. Okay. So suppose this is V in here, right? V in. So this guy is V in here. So this will be V in only, because as we know that from the virtual short concept, V in will be here. Okay. And the V out will be equal to V in, right? Because it looks like a buffer. Okay. There is a, you know, unity feedback is there, right? And this V in is here, right? Here this V in is. Okay, so now we can take this resistive network separately. Okay, resistive network separately. Okay, and here the current will be flowing I in. This current cannot go into the op amp, so this current will go here, I in. Okay, so now can we take this resistive part separately? So let me take resistive part separately. So here is the resistance. Two resistances are there, right? And you can see this is a ground terminal, and this is V in. This is 20K. This is 5K, and This is 10K. And Surajit, have you got the answer?
So it is 17.5.
75 4, right?
17.5, sir.
No, no, no. Actually, answer is 70 by 4.
Yes, sir. 70/4 is 17.5. Yes, sir.
Okay, 70 by 4 means 17 by point 0.5. Yeah, great. Okay, you have got the answer right. So this is how you might have uh, followed the procedure, right?
Yes,
So,
sir. Yes, sir.
so V in will be here, and this is the I in, right? So you can take one. Either if you want, you can Theveninize this, or just to find Vx here. You can consider this a Vx, okay, and then you can apply KCL at this point, right? So by KCL, just I'm writing KCL. So by KCL, so V here you can say V in minus Vx, or you can say yeah, V in minus Vx, right, upon 10 is equal to uh, this current is coming here, right, and this current is going, this current is going, so coming equal to outgoing. So Vx minus V in, again Vx minus V in by 20 plus Vx by 5. From here you can find the Vx. If you will calculate Vx, we will find Vx as 3V in by 7. Okay. Once you got the
Yes, sir.
Vx, you can replace I in. What is I in here? I in is basically V in minus Vx by 10. Now you can replace this Vx with the help of this Vx. Okay, and substitute here. So you will get R in as R in equal to V in by I in, okay, 70 by 4. This is the answer. Okay, kilo ohm. Next question is okay. So let me take one important question where you have to determine the V out. Okay, very good question. The question looks little big, but can you try this question, Surajit, to refresh your concept? This is minus, this is plus, and this is grounded. Okay, and there is a resistance connected that is 5K. Hmm. And there is a resistive divider like this. Okay, and one more op amp is connected here. Okay, one more op amp is connected, right? And this is connected with plus minus, and this guy is connected here. Okay, and you can connect this from here to here, and this is what the circuit looks like, and you have to determine this voltage V naught. This is 3K, this is 2K. Okay, this is 2K. Let me erase this and write down properly. This is 2K, right? And the input here is given as plus 5 volt. Okay, so can you help me to get V naught? The op amp is ideal. Find V naught.
So 1 milliampere current is flowing through 3 and 1K, no, sir?
This is not 1K, this is 2K, right? Let me erase again.
Okay, okay, 2K.
Yeah, because as I told you that this is 2K. Let me write here properly. This is 2.
Yes, sir.
Yes. I'm using thick pen so that circuit can help you to, think differently. Yes. So yeah, please go ahead and solve this question. See, these kind of question can be done within 10 seconds or 40 seconds. Okay, if you have attended my class or attending my class. Hmm. After that, we will start mm, very good topic, that is diode applications. So let us finish this very soon.
Yes, sir. So can you please discuss some in op-amp actually for frequency response part, like unity gain frequency bandwidth? I have little doubt on that actually.
Yeah, we will discuss. We will discuss. Yes, definitely.
Okay, sir.
Yeah. Hmm. All those concepts we will discuss as our need arises, right? So as I said that this is the basic one, then a diode will come, then we will discuss about non-linear part of the op-amp, and then we will come to all those frequency and everything. So don't worry. Uh, Briefly, we will touch everything. And the last
Okay,
day
sir.
we will take only problem solving session. So quickly we will solve many problems from the previous year. So you will see that, oh, how fast we are solving analog questions. Okay. So you will be very okay. Okay. So have you got the answer here?
It's a 5 volt.
Mm. Uh, okay. So you have got, yes, yes, but negative 5 volt is the right answer for this. Okay. This is how one make mistake. So 0 volt will
Yes,
be here.
and
Yeah, 0 volt will be here, and the current will be 1 milliampere, right? And this current will flow here. So this current will go like this. Okay. You don't have to worry about anything, right? Now you can directly uh, you can see here, right? V naught is this, and you're going up, and there is a five uh, you know 5K resistance is there because the current taken here is zero, right? 0 ampere. So the answer directly is -5. Okay, if this current direction is downward, then positive answer will be there. Understand?
yes, sir.
Because you are going up. So please look also like this. Don't apply always KVL, KCLs. Okay, think like that. See, if you're going up and you have to find voltage, right? So you have to take the answer negative here, right? It's okay. Next is this was the question, very important question. Mm, hmm. One more question I wanted to discuss, which I did not discuss here, is that uh, suppose there is a this question minus plus, and this is connected like this. This is V naught, okay, and here you can connect source minus plus 4 volt, and there is a resistance this time connect, that is 0.5K, and this guy is grounded. Let me put the resistances, corresponding resistances. This is 5K, and this is 2K, and this is 3K. This is 3K, right? So please solve this kind of a question. 3K. And the op amp is ideal. Okay. You have to find the output. This guy you have to find. Op amp is ideal. Hmm. So you can get the answer. I will directly give you the answer. The answer will be 50 by 7. Okay. You can solve this question. How you are going to solve this question? Just find the voltage here. Okay. What will be the voltage here? By potential divider, right? This voltage across, you can say V plus will be how much? 2V naught by 5, right? And then this same voltage will be across 5K as well. And then you can go ahead and apply KCL or KVL, whatever you want to apply. Okay. So you can apply KCL at this point, right? You will get everything, right? The current, you can say the incoming current equal to outgoing currents, you will get 50 by 7. Okay, Surajit. Do I
Yes,
need to
sir.
solve this problem? No. Okay. This is how you have to solve. Because you know the node potential, now apply the okay. An important concept here is that the Miller effect. What is Miller effect? Miller effect. See, sometimes what happens, suppose this is a op amp minus plus, right? And it is under Miller effect is always seen, remember always seen for inverting mode, right? Inverting mode. If the op amp is under inverting mode, right? If the input is connected to inverting terminal, then only you have to see the Miller effect, right? Don't try to look for Miller effect in case of non-inverting. This is very important, right? So what is the Miller effect is basically we are going to see here. Suppose this is kind of and op amp is there and there is a feedback network that is G. Okay. If we are trying to find out Z equivalent, right? If we are try to find out the Z equivalent. Okay. So Z equivalent here will be what? And the gain is finite. And the gain here is given as finite gain, right? And the gain is what? A. If the gain is finite, then how you can determine Z equivalent? Okay. And this Z equivalent, okay, will affect the bandwidth of the op amp, right? So because the bandwidth is basically what? The inverse of the time constant. The bandwidth is basically 1 upon RC kind of. Okay. Bandwidth is 1 by RC. Understand? Uh, or you can say 2 pi RC if you are in considering in hertz, right? 2 pi RC. So this R will, you know, will increase or decrease. Okay. So your bandwidth will decrease or increase. Okay, respectively. So we are going to see that. So how to determine this Z equivalent if the gain is finite here A? So as I said to you that you will have to draw what? You will have to draw the equivalent, right? So you can draw the equivalent for that. This is connect there is a V in and the current will be I in. Okay, and this Z will be there because there is a Z. Okay, output part that is V naught, and here sorry, let me raise this part. You can take, and this is a dependent source, okay, which help you to model an amplifier that is plus minus A times VID, right? The difference, and there is a VID, right? This is VD or VID, you can see. Understand? Now you have to see what? You have to see the input resistance from here, or you can say Z equivalent. Okay, so it is very easy. It is very easy now. You can apply. Uh, So if you're going, this current is going like this, so this current will pass through this, okay? Because this is open completely, right? So what you can say here is that you can apply one simple KVL from here to here, here to here, here to here, here to here, here to here. Okay, by KVL. So by KVL, what will happen? You can say this is plus minus, right? Plus minus drop across this, that is Z times I in, and so you can take minus V in. I always take first polarity of this voltage, and here the first one, that is plus Z I in, and then plus AVID, okay, equal to 0. So you can say from here is that you can determine I in. So what is I in here? I in will be V in minus AVID by G. Uh, you have written KVL, but by inspection you can write this V in minus AVD upon Z. Directly you can write if you want to find I in. Yes, this current directly you can write. Needless to write KVL. Okay. Because you know this is plus to minus and this is plus to minus. In network theory, if two potentials are known across any element, suppose this is V1 and this is V2, right? So you have to determine the current. So current will be what? V1 minus V2 by Z. Okay. This is how we follow in network theory. So you have got I in. Now what you have to do? You have to apply one KCL here again. Sorry, KVL here again. So V in equal to minus VID is given. Okay, so you can put there in place of VID, replace VID with V in. So you will get Z in, right? So you will get Z equivalent as V in by R in, V in by R in is equal to Z upon 1 plus A. Z upon 1 plus A. Okay. Okay, Surajit, have you got this Z equivalent? Yes. Hello. You will get Z equivalent like this. Okay. What we have made assumption, or we have applied KVL in the first loop, that was VD equal to minus V. Okay. So always keep in mind some important note, as I told you, is that Miller effect is seen only for inverting amplifier, right? You can write here the Miller effect is only seen for inverting amplifier. Inverting amplifier. Okay. So we in BJT you will see that there are three configuration: common emitter, common base, and common collector. So only common emitter suffers from the Miller effect. Remember, only common emitter. Okay, only common emitter suffers from the Miller effect. These things are very, very important. Nobody knows, right? Common base and common collector do not suffer from the Miller effect. This is the very important note. Please keep in mind. Okay. Very important thing. Common emitter, right? Common emitter suffers from the Miller effect. Okay, Surajit. Great. Yes. So please keep this in mind. Next is suppose you have to find R equivalent for this, right? In the question, they have asked R equivalent. Suppose this kind of a op amp is given minus 100, gain is given, okay, and there is a feedback resistance that is this, and the gain here you can see is finite. The gain here is finite, okay, and you have to find R equivalent from here. R equivalent, okay, and the gain is minus 100. This kind of question you can expect in HAL, small questions, okay. Now, if you want to find Z equivalent, so what is Z equivalent? Z equivalent means Z upon 1 plus A, right? And this negative sign shows that, what? It is inverting amplifier, inverting, okay, amplifier. Understand? So you don't have to take this negative sign now. You don't have to take this negative sign. Directly you can place here. Now this is resistance in case of impedance, right? Because there is only resistance. So 1000 upon 1 plus 100, right? So this is your answer. So 1000 upon 101. You can divide this and you will get the answer, right? So approximately you can say this will be 10 ohm. Okay, so always keep in mind that if there is a negative sign, so don't put here negative sign, right? Already this expression has been derived considering that the op amp is under inverting configuration, right? So this is the first question. The question number second says here is that if there is a inductance connected, okay, so this is basically the minus 1000 gain is given, minus 1000, finite gain only, and this time the inductance is connected, right? So 1 millihenry, and you have to find Z equivalent. So what is Z equivalent? Basically, Z equivalent is Z upon 1 plus A. Already we have derived this. So Z equivalent is this, right? Now what you have to do? As we know that what is the impedance of this inductance? That is J omega L, right? You can say this is J omega L, and L here is 1 millihenry, okay, and 1 plus 1000 because the gain given is 1000. So that is SL, you can say that is SL upon 1 plus 1000, right? Because this is SL, okay. And what is Z
Hello.
equivalent? Yes.
Sorry, sir, I got disconnected actually.
Yeah, I was calling you, but you did not hear me.
Yes, and network issue is there.
Yeah, it's okay. It's okay.
Yes, I will check the recorded one actually
Yeah,
in
no,
that portion.
yeah, no problem. So you just see this Miller effect. Have you noted down Miller effect?
Yes, sir, I have just started that portion, then only.
Okay, great. So see, I'm talking about Miller effect, right? Let me get back. Okay, so Miller effect
Yes,
basically, yeah,
17 kVL up to that I have there
yes.
in
So
the equivalent circuit.
yeah, this equivalent circuit we got to see, and directly we got this Z equivalent, right? So Z equivalent we got here is like Z upon 1 plus this finite gain, okay, A.
Sir,
So this expression you have to keep in mind always. And also I've
okay,
given
sir.
you some important note which many student does not know is that Miller effect is only seen for inverting amplifier. And do not break your head for non-inverting amplifier, right? So bandwidth and all, everything will be taken, I mean, whether it will increase or decrease. So you have to see, you have to check for inverting amplifier, right? And the gain should be finite. Gain, if there is a gain finite, then there will be Miller effect, right? Uh, and
Yes, sir.
in case of BJT, there you will study three kind of configuration: common base, common emitter, and common collector. So only common emitter suffers from the Miller effect, right? Common
Okay, so
emitter
why
only.
not common base?
Uh, yeah, why not common base? Yeah, it is a good question, but in case of common base, what is the input resistance in case of common base?
In case of common base, it is low, sir.
Yeah, it is low, already low, right? In case of common emitter, the parameters like input resistance and output resistance have everything, they are of intermediate range. So when we go to high frequency, okay, when we go to high frequency, right? So the accordingly the various capacitance comes into picture, right? Uh,
Yes, sir.
yeah, so accordingly the bandwidth gets changed, right? So we will see why common base and common collector does not have Miller impact, okay? When we will
So for
discuss,
common collector, as the voltage gain is 1, so that factor 1 minus 1 is this, I mean 0. So for that,
no, no, not like that.
okay.
In case of common base and common collector, yes. What is the gain? Can you tell me what will be the gain here in case of common base and common collector? Suppose voltage gain you consider.
Yes, sir.
It
So
will
for
be
common
having
collector,
inver
this unity in here.
no in case, yeah, in common collector, is there any inversion in case of gain? Is there any 180-degree phase shift in case of common collector when you determine the gain of common collector amplifier? No.
Common collector. No, sir. No. Yes.
No, yes,
No, sir.
right? So there should be
Yes, sir.
180-degree phase shift, just like inverting amplifier. So you always recall inverting amplifier, right? If there is an inversion, in case of common emitter, there is an inversion, right? So in this manner, we can keep in mind. Okay.
Okay, sir.
Yeah. So in the examination, if the question will be there in HAL, so you can answer this kind of a question. But we are just touching of the topic. We are not going into details. So for the present, keep in mind this, okay? And we'll discuss frequency counterpart, frequency response counterpart. So you will get to know everything, right? Okay. So this is the circuit given, and you have to find R equivalent, okay? And there is a gain minus 100. There is a gain minus 100, and this is 1000 here, right? So Z equivalent means Z upon 1 plus A. Now this resistance is just an impedance, right? There is no frequency and all, so you can treat it as resistance only, 1000 upon 1 plus 100. Don't consider this negative sign now. Why? Because this negative sign shows that you are under inverting, okay, mode, okay? Just take positive part of that. Understand?
Yes, sir.
Many students make mistake here. They put minus here, right? Because this expression already contains, right, all informations, right? Information about inverting stages. Hmm. And now there is a Z equivalent as there is a Z as inductance, right? So that is SL, Z omega L, right? So what is Z equivalent here? That is SL equivalent, right? SL equivalent. So this S and this S will get cancelled. What is L equivalent here? L equivalent here will be L upon 1 plus 1000. So the way you calculated for resistance, the same procedure you have to follow for inductance. What is L here? L is basically 1 millihenry, 1 millihenry upon 1 plus 1000. So now it will give you 1 microhenry. Yes, because 1000 will go up and it will give you approximated answer. On
Yes, sir.
this, so don't try to use calculator as well whenever 1 and 1000 you are comparing. One of the very important concept here is the in case of capacitance. If capacitance is present here, this is very high this time. That is 10 raised to power minus 10 raised to power 6, you can say, right? And 1 microfarad, and you have to determine Z equivalent. So the same procedure you have to go ahead. Z equivalent means Z upon 1 plus A, right? So what is Z equivalent? 1 upon SC equivalent, right? Because in case of C capacitance, we get as 1 by SC, right? So 1 by SC equivalent will be here and Z will be 1 by SC 1 plus A. Okay. So what is C
Yes, sir.
equivalent here? Can you tell me what is C equivalent here? C equivalent here will be 1 plus A by C, right? If you will compare here. So this guy will get cancelled SS, or C equivalent will be here. C equivalent will be 1 plus A by C, right? Understand? Now,
Yes.
this A can be, this one can be neglected, right? This one can be neglected.
So 1 plus A into C, na?
Yes, yes. 1 plus A into C, right? Yes. Yeah, 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 it is true. Because this one bit, 1 minute. Yes, 1 by C will go down. Yes. So it will be C times 1 plus A. Very good. Okay. Yeah. So this is what the capacitance, Miller multiplication of the capacitance, right? So this is called Miller multiplication, right? So C equivalent is basically C times 1 plus A, right? That is known as the Miller multiplication. Miller multiplication. So you have to keep this in mind, right? Miller multiplication. So whenever C is given in the feedback, so you can multiply with the A, okay? So what is C equivalent here now? C is given as what? C is given as what? 1 microfarad, right? 1 microfarad, that is 10 raised to
Yes.
power minus 6. And now you can neglect 1, man. You can neglect 1. Why? Because this guy is very high. 10 raised to power 6, right? So 10 raised to power 6. What is this? 1 farad. So capacitance value has got increased. If the capacitance value has got increased, so what will be the bandwidth? Bandwidth will decrease, right?
Magnitude reduced.
Yeah. Yes, yes. So if I talk about any STC network, STC, I mean to say single time constant network. So if I talk about any STC or single time constant network, that is simple RC circuit, right? This is very, very important circuit. First order, this is known as single time constant circuits. Okay.
Yes, sir.
Uh, Also known as low pass filter, right? So these things you but in reference books these concepts are given, right? All these names and all, but mostly people keep in mind with the help of transfer function and all. But by looking at the circuit, you must be able to tell, okay, this is a single time constant because there is only RC. Okay. Hmm. So if there is a RC here and if any input is applied, some sinusoidal is applied, such as Vm sine omega t, you can say Vm sine omega t. This is R, this is C, or you can say 1 upon j omega c. Okay, 1 upon j omega c. Let me erase this omega properly. Let me write 1 upon j omega c, right? Yes. So, as far as we know that the tau is here the RC, right? The tau is RC. So the bandwidth will be what? The bandwidth will be 1 upon 2 pi RC. Okay. If the frequency is high, then this capacitance will be what? This capacitance will be short circuited, right? And if the frequency is low, this capacitance will be open circuited. So it will work like a what? It will work like low pass filter, right? Low pass. Understand? So the plot which we will get here is the gain plot here with respect to frequency. You can say V naught by V in will with respect to omega will be looking like this. okay, like this, low pass, okay, and 3 dB frequency from here to here you can determine that is omega 3 dB will be 1 upon RC, okay, or so bandwidth is what? 1 by tau, right? Or you can say 1 by RC in radian. Remember radian per second, okay?
Yes, sir.
Or you can say 2 pi only, 2 pi RC. So if C equivalent will be increasing, right? So if C equivalent will increase, then what will happen? Tau will increase, right? Definitely tau will increase. Here you can see this is C equivalent only, you can say. Okay. If this guy is increasing, this tau will increase and the bandwidth will fall, right? So this bandwidth will be here then. Okay. Bandwidth will decrease. So remember that this is what the Miller effect is. So in case of inverting amplifier only, Miller effect comes into picture. And in case of common emitter amplifier, this comes into picture, right? Please keep this in mind. This is what I wanted to discuss. Why we call 3 dB and all, you know. Hmm. Okay. Let me take one important question for finite gain. Whenever the gain is finite, okay.
Sir, we actually
Hmm.
means actually we want Miller effect, means Miller effect is good or bad, sir? Means I have a confusion in that case. Or you want to avoid Miller effect in the circuit?
Actually, we can't avoid Miller effect in the circuit, right? Because how can you avoid if we are in inverting mode, right? See,
Yes, sir.
yeah, you are talking about whether it is positive or negative, right? If there is a Miller effect, definitely if your bandwidth is decreasing, right? So suppose somewhere you want that much bandwidth, but the bandwidth is decreasing, right? So there is a problem, okay? So in case of communication system and all, we want trade-off between the gain and the bandwidth, right? We want high
Yes, sir.
bandwidth sometimes, we want low bandwidth sometimes. So yeah, sometimes it can be detrimental to us, sometimes it can be beneficial to us. So depending upon the situation, okay, where in which
Okay.
where you are working, or depending upon the application, I would say, right?
Yes, sir.
So
So, for example, if bandwidth is reduced, so we can neglect the high frequency effect of noise, na? So, I am confusing, is this good or bad? Okay, Miller effect. That's why, sir.
okay, you are saying that if there is a noise, so we can neglect noise, you are saying.
Yes, sir.
Noise is basically what? Noise is having high frequency, okay?
Yes, sir.
So it is already rejected now because high frequency cannot be passed through the low pass filter if we are connecting. Okay.
Okay, okay, that's point is true.
Yeah, low pass filter means what? Low pass signal. And noise is, in case of op-amp, noise is always eliminated. Why? Because noise is a common mode devil, right? Suppose this is a op-amp and there is a signal plus noise and minus signal plus noise, right? Because this is plus and this is minus terminal. So what will be output? The difference between the two, right? So signal plus noise
Yes, yes, sir.
plus signal minus noise. Okay, so signal noise gets cancelled. So you will get the signal only. That's why we go for differential measurement. Okay, in case of a differential amplifier, this is the differential measurement, right?
Okay, okay, sir. Yes, sir. So, first test should be always differential amplifier, na, sir? For
Yeah,
any instrument.
yeah. For any, that's why op-amp is mostly used today in the world because low noise amplifier. Have you heard about low noise amplifiers?
Yes, sir, in communication receiver actually.
Yeah, LNA kind of, right? So
Yes, sir,
there
yes, sir.
also we use op-amp only, differential stage, right? So though in practice we can't neglect noise, okay? Suppose I'm teaching you and somebody is any BMW is passing from nearby, right? So we can't neglect
Mm.
that noise now. We will definitely see,
Yes,
okay, there is a noise. But for the HAL examination, only we need to understand how this bandwidth is affected and where we can see the Miller effect and all. In most of the class, nobody discussed this much. I just am telling you, highlighting you so that you should understand how analog circuit is studied properly, right?
Yes, yes, sir. Yeah, I'm
Exactly.
actually also preparing for interview also for MS MTech.
Okay, so
So
what is your
also,
rank?
so my rank is 820
Great.
this year.
And what is your score then this time?
The score is 610.
Okay, if you have if you might have scored around more than 700, so you might get IIT Madras Texas instrument, right?
Yes, sir,
But
yes, sir. So this year score was very down actually with respect to
yeah, exactly.
ECE actually
Yeah, the paper was quite
compared to
good.
last.
Yeah.
Yes, yes, the paper was very good. Yes, yes, sir.
Mm.
I got some very silly mistake in this way because
No,
but uh, I should have expect around
yeah,
55 to 60 marks, but for the my marks is 48 actually, sir.
okay.
I I got hell of lots of I mean very silly mistakes is happening.
Right. So let us solve this problem. Definitely, yeah, you have great concepts. You can get good IITs, in fact, by cracking interviews. Okay. So, but you will have to pass through these things. You can go for IIT Madras normal MS, right, under Pawan Santi.
Yes, sir. I'm thinking about MS only.
Yeah, analog circuit design. So you will get to know these kind of questions, what I'm discussing, right?
Yes, sir. Yes, sir.
3K. The way I'm solving the question, the same way they like to all students to solve the question. So see, 3K and 1K, and AOL is what? AOL is this time finite. Okay, that is 10. And find you have to find what? V naught, right? You have to find V naught. Now, uh, as far as this is concerned, right? As we know that what is V naught in case of any op amp, that is AOL times V plus minus V minus, right? Or you can say VP minus V negative. Okay, understand? So what is V plus here?
Yes, sir.
V plus is 2 volt. And what is V negative? You can determine by using what? By using, you can't apply now the virtual short concept and all, right? So remember this, you can't apply virtual short concepts. So without drawing equivalent, I'm telling you the answer, right? So the V naught will be here, V naught by 4, right? From here to here. So these lecture will be helpful for interview as well. The way
Yes,
I'm,
sir.
yeah. So V naught by 4 it will be, right. Now you can keep here. Yeah, Sri Hari is also joining us, right? So the V naught is equal to that is 10 times V plus. What is V plus? 2 minus this is V naught by 4, right? So from here you can get the answer. Okay. So what is
Yes,
V
sir.
naught? What is V naught here now?
So 40 by 7.
Yeah. See how I'm answering the question in single line, right? V
Yes, sir.
naught is 40 by 7. Otherwise, what many will do is they will draw the equivalent for this and waste time. Okay. So this is the answer. Very good. Next is you can find, okay, next questions. Various questions are given. So this is how OPAM part 1 is over. OPAM part 1 is over, right? OPAM part 1. And hope you might have liked all solution the way we solve the questions, right? Now we will start diode applications, and Sri Hari is joining us, so once we start new topic only, right? So diode application. So please Sri Hari, watch everything from the recorded one, right? Once it will be link will be given. So diode application now we will start, which is very important because for OPAM part 2, we need some nonlinear elements such as diode. So diode is basically a two-terminal device. As I said that I'm not going to discuss the physics inside the diode, right? Or semiconductor physics inside the diode. So suppose this is a diode, simple diode, right? It is a two-terminal device. So diode is a two-terminal device. Diode is two-terminal guy, right? Okay, right. Sometimes this pen, you know, it's okay. Diode is a two-terminal device, you can see. So die is there now. Die means two, and there are two electrodes. Okay, so one is anode, another one is cathode. So only two things you have to keep in mind. I'm not specific right now for semiconductor diode and all. Just consider this is a symbol of diode, and you can see this is P and this is N. Okay. So the very important point which you have to keep in mind is that, okay, if a diode is forward bias, okay, when you can say the diode will be forward bias, okay, when anode potential is greater than the cathode potential, right? When anode potential is greater than the cathode potential, then only you can say the diode is in forward bias, okay? So let me draw the IV characteristic for you guys, and right now I will be taking only the ideal diode characteristic, ideal diode, okay? Ideal means what? If the diode will be in forward bias, so it will be replaced with short circuit, right? And if the diode will be in reverse bias, it will be replaced with open circuit. That is called the ideal case. In fact, this time in the gate examination, question was given from ideal diode only, right?
Yes, sir.
Yes. So the IV characteristic which I'm going to draw is similar, which was given in the gate. So if this potential, if anode potential is greater than the cathode potential, then this diode will be in forward bias. Okay, so you have to keep this in mind. Then the current will flow. Okay, suppose the voltage here is 0 across this diode. Okay, if the diode is on, the voltage across the diode will be 0 because this will be replaced with short circuited, right? Short circuited. Okay. So you can say that there will be current flow, right? So current will be flowing like this. Okay. This is a IV characteristic, right? The voltage applied is V and the current is flowing I. So this is how the IV characteristic look like for forward bias, right? And the equivalent of a diode will be short circuited, right? And here the cut-in voltage is 0. Okay, we are not considering any silicon semiconductor diode or germanium diode, right? I'm just considering ideal diode. If anode potential is greater than the cathode potential, then the diode will be replaced by short circuited and the current will flow. So this is how, and the current should be positive, and the current should be positive in case of forward bias. These two important information you have to keep in mind. And if the voltage across, if the polarity is changed, right? If the voltage across the diode is minus to plus, right? If negative potential is applied across the uh, to the positive terminal, right? So what will happen here is that the diode will be replaced by short circuited, right? And the current will be 0. So this is the reason which exhibits reverse bias condition, right? Which exhibit reverse bias condition. Okay. So please keep this in mind. And the diode status will be what? Diode status will be open circuited. These two important information, if you know, you can solve any question, right? Yes. Srihari, have you understood this? And Surajit?
I think he is left.
Yeah, I think he might be facing some problem of internet only.
Yeah,
So
network issue.
yeah, that is what the main problem is. So diode is very easy. Right now I'm talking about diode only, right? And you have to, two conditions, right? The first one is if the anode potential is greater than the cathode potential and the current is greater than zero, that is the forward bias. Okay. And second one is if the VA is less than VK, so current will be zero, right? And then this is reverse bias, or you can say that the voltage across the diode is negative, right? If the voltage across the diode is positive, then this will be happening. And the status, that is what the basic requirements and nothing else. Now let us check example number one. Let us check whether the diode is in forward bias or not, and then find the current. So check whether the diode is FV or not and determine the current. Okay, so whatever problem I'm taking is from Sedra and Smith only, right? So these problems are very good problems, right? Just to start with. So number one problem is what? By looking at the question, you can see, right? So right now I'm just considering ideal diode. So don't worry about those cut-in voltage and all. Okay. If nothing is mentioned, then consider ideal diode, right? 3 volt.
Yes, sir.
Hmm. And this is current I. So can you tell me whether the diode is on or off in this case?
Yes, sir, on.
Yeah, because you have to see these two potentials, right? 6 voltage is greater than 3 volts. So yes, this will be on and the diode will be replaced by short circuited like this and the current will flow, right? That is 2K. You can say that the I will be 6 minus 3 by 2. It means that it is what? The 1.5 milliampere, right? So sometimes many people apply KVL here as well. So don't do like that. Just understand how we write direct, how we determine current directly. Two potential are known. Okay. Suppose this is R and this is V1, this is V2. If somebody wants current I, so I will be what? I will be V1 minus V2 by R. Okay. Chalo. Second question. Check whether the diode is forward bias or not and determine the current. Same under same heading, you have to check. This time the diode orientation is different. This is minus 5 volt and this is 8 volt and this is 2K. So Surajit, please tell me what shall be the current here. Current should flow in the direction of diode only from P to N, right? Can you tell me?
Yes, sir, diode on in that
Diode
case
on,
also.
right? Yeah, because this potential is greater, right? Yeah, greater.
Yes, sir.
Mm. So here again I will be minus 5 plus 8 upon 2K. So I think the answer will be same here again. That is 1.5 milliampere. Third. Uh, Great. Suppose let me put one voltage divider here and this 10 volt is dividing here, that is 5K and 5K potential divider, and there is a diode connected to it, right? 3K and this is, okay, there is 2 volt, right? So now you have to determine whether diode is on or off and then find the current, right? So this kind of question is very easy, right? Okay. See, whenever this kind of questions will be asked, so what you can consider that you can consider or make assumption that your diode is on only, right? Assumption क्या रहेगा? Assumption will be assume that diode is on. So you replace it by short circuited, right? And then find the current I. I must be what? I greater than 0. If I is greater than 0, then assumption is correct, right?
Yes, sir.
Understand these important information you have to keep in mind this. But for the present here, you will have to simplify this network. So this network is quite good network, right? So you have to look back from here. So what you have to do? You have to Thevenize this. Thevenize. How we have to Thevenize? Thevenize in the sense that you have to forget about this part. Just forget this, right? And take this network only. And look from here. This is 5K. This is 5K. And this is 10. So find out what? The VTH and the RTH, right? What is VTH? VTH will be divider, right? The 10 will be
So
divided
5 volt.
into, yeah, that is 5 volt. And what is RTS? RTS will be 2.5, right? And now connect the diode back. Now connect the diode back. The diode connect the diode back, that is this. Very easy. So this is 3K. Now you can directly tell whether the diode is on or off, right? If you know the potential. 2 volt. Yeah, definitely diode is on because this potential is greater than this potential, right?
Yes, sir.
Simple I. Now you don't have to replace anything. Directly you can write I. I will be what? 5 plus 2 minus and plus 2 minus. So 5 minus 2 upon. If there is a plus here and minus here, so you have to take plus. 5 minus 2 by 5.5. Okay. So you will get the answer here. So I will be what you are getting I here as. Hmm. I will be 6 by 11, right?
Yes, sir.
Milliampere. So see, I'm solving this question in one line, right? But most of the student, what they will do, they will solve the question here by applying KCL, right? They will consider Vx here, then apply KCL, then base time, okay? So always take the help of these theorems, very important theorems, right? And don't forget to calculate R equivalent. Sometimes people make mistake here. They calculate only what potentials, and whenever they want to find current, they forget that resistance R equivalent, okay? So don't forget that. Understand? See, single line answer.
Yes, sir.
So don't follow method 2. Method 1 is workhorse. And whenever you will go for written exam, so they will see your the way you solve the questions. The way teacher is solve the question from where you have studied will not matter. The way you solve the question matters. Okay.
Yes, sir.
Next question. Suppose the question says here is that just ideal diode I'm discussing, ideal diode, and uh, the method I have told you is that just consider or make assumption that all the diodes are on and find out the current. If the current is positive, then your assumption is correct and answer is correct, okay? And if the current is negative, then your diode is off and your answer will be 0. Understand? That is what the procedure is. Hmm. This is 8 volt plus minus 1K, 1.2K, right? And the diode is here, and this is resistance here, and this is connected here, right? You can say this is 5 volt, and this is 3, right? and this is 1.2K, right? So what you have to find here is that whether diode is on or off. And if the diode is on, then what is current? If diode is off, what is current, right? So what you have to do now here is you can apply Thevenin equivalents, no problem. You can apply Thevenin.
Is it 1.2 or 112K?
It is 1.2.
Okay.
Yeah, the stylus is not permitting me to write dot here. Okay, to
Okay,
create
sir.
confusion, yes. Q equal to I mean, this is the question, and now you can determine Vx here, right? And then Vx minus 5 upon this 3, right? So what assumption you have to make? Assume that diode is on. Whenever you make assumption, you have to prove as well, right? And prove I must be equal to 0. अगर ये नहीं होता, if I, okay,
Yes, sir.
these things you have to keep in mind. If I is greater than 0, then assumption is correct. If I is less than 0, then assumption is wrong. Okay, and I answer will be 0, right? So these two important points you have to keep in mind. Hmm. So just apply, and it is very easy. Or you can Theveninize as well. I don't have any problem. You can Theveninize this. Okay. Okay. You can Theveninize. So whether you Theveninize or just find out VTH and RTH. Okay. And there is a diode. This is 3. I think Thevenin is very easy, right?
Yes, sir.
Applying KVL, KCL sometimes gives you very bad.
It takes time, sir, actually, writing KVL.
Yeah,
KCL, actually.
KCL, yes, yes. Yeah. How do you solve the problem? How you would have solved the problem? Like applying KCL only or Thevenin?
Sir, it depends in circuit, actually.
Oh, great. So this guy is 8 times 1.2 upon, this is 1000 plus 1.2, that is 2.2, right? So please write 2.2 here. You can tackle this 2.2, and your RTS will be what? Your RTS will be 1.2 into 1 upon 2.2. Okay, K only. So you will get the answer here now. So based on VTS, you can say that the diode is reverse bias only and our assumption is wrong, right? So what is VTS? Can you calculate VTS? The VTS comes out to be here is what VTH you are getting here? That is 58 by 13, I think.
Yes, sir, 4.36 volt.
Yeah, 4.36, right? And this guy is off. So VTH is less than 5. Therefore, assumption is wrong. Okay. Assumption is wrong. And I will be what? I will be 0. Right? Answer will be 0 and diode will be reverse bias. Diode will be reverse RB. So very quickly you can solve. I will take some ISRO question as well in the next class. And you will find this is workhorse. Next. one important question where most of the aspirant make mistake. This is 3K, 6K, right? Plus 5 volt. Guys, don't keep in mind those things like open circuit test, short circuit test. Okay, those bookies, gyan bookies language, right? That is time waste. Okay. Hmm? That is the way to attract people, right? That's it. That is not the just go some smart method. Okay, that is 3K and 6K, and this is 6K and 3K. Now tell me the I. This is a very good problem. So Surajit, what you will do here? Can you tell me how you will determine I?
Using Thevenin's equivalent
Yeah, great.
right and
Yes,
left side.
yes, yes, yes. Great. So most of the student, what they do is they apply open circuit test, right?
Yes, sir.
Then
So by open circuit test, we can tell the condition of the diode is it on or not. But
yes,
finding
yes,
current we have to do.
yes. That's what I'm saying, na. So suppose in the question they are asking I, and you know only open circuit test, right, and short circuit test.
Yes, sir.
So testing is what? Just make assumption that you're good guy, right? And the proof will be in front of you after get result, right? Means you are intelligent.
Yes, sir.
If intelligence, if his score is not good, means we are not intelligent, right? Okay.
Exactly, sir.
So that is what the main thing is. So you can make, I think it is very easy. So, ATH, RTS will be same for both. That is 2K. Okay. I think 2K is the RTH. Yeah, 2K is the RTH and VTH. What is here? That is 5 into 6 upon 9 and 9 into 3 upon 9. So 3 volt here. Uh, yes, there is a 3 volt, and this is what? This is 15, I think, right? Let me check. That is 5 or 15. No, this is 9. Yeah, this is 9. Yes, sorry. This is 9. Surajit, please correct. This is 9. Okay.
Okay, sir.
So this guy is 9 now. 9, 9 gone. That is
Then
6.
value is coming easily, sir.
It is, that's why the question is like this. And it is very easy, like 3 by 4, 0.75 kind of guys, right? This time answer was also 0.75 in the gate exam, right? In that small signal questions. Mm.
Yeah, yes, yes.
Yes, so please tackle this, right? Very good questions. Uh, I will solve that question for you, small signal. You will see that how I'm solving the question. So very easy within 20 second or 10 second. Okay, so this is what the first kind of diode problems, and the second kind of diode problem will be here, like based on the digital gates, right? So you have to find V naught, right? And the diode you have to consider is ideal. Diode you have to consider is diode is ideal, right? So if we are considering digital gates here like this, the other digital gates, right? I mean, this is one digital gate only using diode we are making. So this is V naught, and this is 1 volt, 2 volt, and 3 volt. You have to find output voltage, and you have to find current through this, right? I. So This kind of a problem is solved by how you solve this problem. This is D1, D2, and D3. Can you tell me the procedure? What kind of, like in the first post part of the question, a first kind of problem of a diode, we said that we have to make assumption that all the diodes are on and find out the current through that. If the current is positive, then the assumption is correct. If the current is negative, then the assumption is wrong, and answer is 0. In this kind of a problem, okay, this type of a problem, what you have to do here is you have to find the potential across each diode, okay, potential across each diode with respect to reference, okay. Find out the potential across each diode. Let me write here. Find out the potential across each diode, okay, with respect to reference. Here the reference is ground. Sometimes the reference will be supply as well. And then whose potential is greater? Whose potential is maximum, right? That diode will be on. Right? Then that diode will be on. Okay, this is very important. And rest of the diode will be off. And rest will be off. Off in the sense reverse bias, open circuit. So this is a condition you have to apply always in this kind of problem. Understand, Surajit?
Yes, sir.
So can you see here 3 minus 0, 3 volt, right? Here 3 volt, here 2 volt, here 1 volt. So which diode is on? D3 is on, right? D3 is on. So V naught will be 3 volt. Understand? And the I will be 1 milliampere. Any problem? Have you got the answer now? V naught is 3 and I is 1 milliampere.
Yes, yes.
Yes. So you don't have to find anything. You can find plus minus, plus minus, plus minus. The potential across this D3 is high. That's why D3 is on. Rest of the, this is the procedure I am telling you. That's it.
Yes, sir.
Next, one more problem is there. Uh, Suppose this kind of problem is there. This time the diode is pointing toward input, because you might have seen this kind of circuit in digital gates, right? 3 volt, 2 volt, and 1 volt, and 4 ohm. Okay, all these problems are taken from Sedra only, right? Sedra and Razavi. Two books are very good, Razavi and Sedra.
Yes, sir. I followed Cedar Smith.
Yeah, Razavi is
Sir,
one.
there is any answer key in Cedar Smith?
Yeah, but we don't have new answer. Okay, we have fifth edition only.
Okay, in exercise, there's a lot of question, but I am not getting the surety about the answer what I have done.
Yeah, yeah. I will share that if you want fifth edition answer. We will. Okay. 3 volt, 2 volt, 1 volt, right? And this is now,
Yes, sir.
now you can tell the status of a diode D1, D2, and D3. So very easy. This time the reference is 5. So 5 minus 3, 2. This is 3 and 4, right? So yeah, D3 is on, right?
Yes, only DG on, yes, sir.
And V naught is 1 volt directly, right? And the current you can determine now. I will be what? I will be 5 minus 1 upon 4, that is 1 ampere. Any problem? So this kind of problem you can solve, right? Here you can say potential is huge, right? Potential is large. and these will be off, right? This will be on. So this is one kind of a problem. One more problem which I want to take up here is the example of Cedra only. That is, this is the diode connected here. Very good problem, right? That is D1, and this is 10 K. And my method works well here. The way we solve the problem. That is minus 10, 5K. Don't waste time, right? Don't waste time. According to me, don't waste time. This is uh, plus 10 volt, and this you have to find V naught here, and this is the diode D2, this is diode D1, right? You have to find the
Yes.
current from each diode, and you have to test whether diode is on or off. How easy? So method one is what? The assume all the diodes are on, right? Assume D1 and D2 on. Okay, and find ID1 and ID2. This is my assumption, man. This is my assumption. So don't think that this is correct, right? Assumption is that, then you have to prove. You have to find the current. So let's,
So D1 will be on and D2 off, no?
yeah, we will see, we will see. Just initially you have to consider both are on, right? So just on, I have replaced this short circuited, and very easy problem. This is minus 10 volt, and this guy is also on, no problem. So everything is short. Forget about that V out and all, plus 10. This is minus, this is 5P. Now what you have to do? You see here that is 0 volt here, right? What is the current here? Current will be 1 milliampere, right?
Yes, sir.
Current will be 1 milliampere. And what is current here? 2 milliampere, right?
2 milliampere,
Yeah,
yes.
10 minus 0, 10 minus 0 by 5. So what is current here? 2 milliampere is coming, 1 milliampere is going here. So 1 milliampere will be going toward the ground, but we want to find, towards 0, right? So here 1 milliampere current will be there, right? Minus 1 milliampere. Understand?
Yes, sir.
Therefore, ID1 is coming out to be 0, less than 0, right? So assumption is what? Assumption for D1 is wrong. Okay. Assumption for D1 is wrong, and that's why ID1 will be 0 always, and D1 will be off. Okay, remember, D1 will be off
Yes, sir.
and D2 will be on. So for D2 will be on. If the D2 is on, then what will happen? You will have to again draw the circuit. D2 is on, then draw the circuit like this, minus 10. This is 10. This is 5. This is 10. And find out the ID2. What is ID2 now? See, this is 10 plus 10 by 15. That is 20 by 15A. So 5 4 ja and 5 3 ja. Right? 4 by 3 milliampere. So any problem is there, and you can determine V naught as well. Okay.
Yes, sir.
How I'm getting this? This is minus of minus 10. So these kind of mistakes you have to avoid. That's it. Otherwise, now you can solve this problem by interchanging 5K and 10K, right? Here it was 5K, here it is 10K. Now you can interchange and see what answer you are getting, right? So you can interchange it. Suppose giving you the problem here. You can solve this problem, right? This is diode, and so see the status of a diode then, right? So sometimes resistance also tells you whether diode is on or off. Like by looking at the values of resistances, you can determine, because you would be able to figure out, the current, right? Based on the higher resistance, low current. Okay, 10K minus, sorry, this is this time 5K. Just you can frame out questions by yourself, no problem. So this time this guy is 10 only, 10 volt, and this guy is 10K. This is D2 and this is D1. So what do you comment on the status of a diode? Yes, Surajit. Suppose diode is on, right? What is current here? Next, let us go to next page. Suppose D1 and D2 are on, right? So replace it by, this guy. Yes, this is minus 10 volt, 5 directly connected, plus 10 volt. Okay, and this guy is 5. This guy is what? 10K, right? Yes. This resistance is 10K. This is 5. So now you can determine this is 0 volt. What is current here? Current will be 2 milliampere. What is current here? 1 milliampere. 1 milliampere is coming. 1 milliampere is 2 milliampere. So here what will happen? 1 milliampere is coming, right? So you can see that this both diodes are on this time. Understand? Both diodes are on, and assumption is correct, right? It's correct. Okay. Understood, Surajit, till here?
Yes, sir.
Great. So catch up the way I solve the question, that's it. And nothing is new here. Already you know everything, right? The very last, but not the least, I'm going to discuss is you have to determine, uh, find the minimum voltage, the very last question. Find the minimum voltage V in for diode to be in forward bias. Find V in. Okay, find the minimum voltage V in. Sorry. Find the minimum voltage V in for the diode to be in forward bias. Okay, so there is a diode. There is a diode, right? This is the input V in, which you have to find out. Minimum means what? Minimum voltage means what? The diode will be forward bias, right? So you can consider that the diode current should be positive or greater than or equal to 0. Okay. So at least the current should be, you have to consider that the current should be positive. It should not be negative. So you can consider I equal to 0 for the minimum, and you can get the answer, right? But anyway, let me uh, 500, and there is a diode connected to it, and there is a supply that is 7 volt. Okay. We will discuss small signal counterparts and everything in the next next lectures. Okay, when we will discuss something related to actual semiconductor diode and the IV characteristics 600 ohm. Right now we are discussing just the ideal case, right, of a diode. Huh. So this is what the picture is, and you have to determine the minimum voltage V for the diode to be on, right? So initially you can consider that the diode is on only, right? If the diode is on, so you can apply KCL at this point. Okay, the diode is on, that means that 7 voltage will be here, right? The diode is on and the current is flowing I is greater than or equal to 0, you can say, right? So you can apply KCL by KCL, because in the question they have mentioned that the diode is on only. Okay, then only you will be able to find the minimum voltage. So 7 minus 15 by 500 plus yeah, this is what the current outgoing, everything is outgoing, right? So you can say that this is plus I plus 7 minus 3 upon 600, right? Yes, equal to 0. So this is what the now there are two variables, right? But this variable, this I can be replaced with 0, okay, for minimum voltage, right? For minimum input voltage, as far as the diode status is on, so I can be replaced with 0. You can say that this is minimum now. 7 minus V minimum or V input, you can say. V input by 500 is equal to minus of 4 by how much? 600, right? So 0, 0, 0, 0 cancel and equate this. So what you are getting here, V? Yes. Hmm. So you are getting V as greater than 10.33 volt, right? After this voltage, your diode will be on, definitely on, right? Have you understood this? So in the
Yes,
next,
sir.
yeah, in the next lecture, we will talk about, let me tell that, we will talk about transfer characteristic of a diode. Transfer. This is also important in the gate examination or in HAL, in IES, everywhere. Transfer characteristics. What is transfer characteristic? V out versus V in, right? And IV characteristic of a diode. IV. What is IV characteristic? I versus V. This time in the gate examination, only two characteristics we always discuss in circuit. Okay. So this was all about today's class, and tomorrow I will also discuss about clipper. I will also discuss about clampers and peak detector. So don't worry, these are not the tough topic. Whenever you attend my class, I will not make you around here and there. I will directly talk about the concept, right? So the moment you will see questions based on clamper and clipper, within 10 seconds or 50 seconds, you can handle those questions, right? It's okay, Surajit. So if you have any doubt related to today's class, you can ask. Otherwise, we will end here. Thank you.
No, sir. So you have told me to find the reason why we use instrumentation amplifier.
Yes, yes, yes. So what answer you have got?
Sir, I have checked once video. In that case, uh, I don't understand the total meaning, but I only understand ki because in the first stage, as their noise is coming,
Mm-hmm.
so maybe sometimes for variation of internal resistance, CM
Mm-hmm.
will be less. So because common mode gain will be increasing
Mm-hmm.
somewhat in that case. So we have to increase the CMRR
Mm-hmm.
by getting two inverting stage in the differential amplifier by making in. instrumentation amplifier. What I
Yeah.
understand is this, sir.
Okay. So, as you have seen somewhere, so this concept is also correct, but I will let you know the exact reason, the exact application. Actually, if you will better tell someone the application, right? Okay, instrumentation amplifier will be useful in these applications, these key areas, right?
Okay.
Because maybe the person who is asking to you do not know about CMRR, right? And if you
Yes,
will
yes,
say
I mean,
CMRR, suppose in the interview I'm going to ask you, right, what is the instrumentation amplifier? I mean, what is the application? And also you will tell CMRR, and also I will ask what is CMRR. Then you will say the sir common mode gain, and also I will ask what is found. So the interview you will be in loop, right?
yes, sir, correct.
So speak though, yeah, it is correct. No problem. Whatever you know, that is correct, right? So we
Yes,
will
sir.
discuss diodes and all. Okay. Thank you so
Okay,
much
sir.
for today. We'll meet in the next class, right? Thank you.
Okay. Thank you, sir.